an eraser if you're allowed to change your mind, but tomorrow we will not do the eraser transportation service because you can use a pencil, it doesn't have to be ink. If it's a pencil that is black enough, some are very thin, they're risky, but if they are black enough, it's okay, then it's easy to erase. In the MAC layer, you have seen in Wireshark MAC addresses, so this is not new. The main thing to understand where it comes from is the original idea of the MAC layer is this broadcast system, and in order to know who should receive the message, you put the MAC address and the destination field. They are sent in the field, in principle, unless you do MACsec, that we will discuss a bit. Which means that it is possible to sniff traffic, which is what we do with Wireshark. You can see packets if you are in a shared video LAN. But of course, if you're in a bridge, it's a bridge network, bridge equals switch, remember, then you will of course not see the packets unless you are on the port at which you're doing packet sniffing. There's a special address for broadcast. We've seen one example, ARP. When ARP is used with IPv4, in principle, an ARP request is broadcast. This is seen by having a destination address with all bits equal to 1, which in XIB is F everywhere. A broadcast packet is supposed to be received by everyone. Broadcast packet exists. ARP is one of them. There are other protocols that uses them. In IPv6, we try to not use broadcast, as IPv4 this is used extensively. And this is one of the main differences between a local area network and a network with routers. Inside a LAN, for good or bad reasons, there are lots of broadcasts. Now, broadcasts are bad. They are bad for several reasons, but the idea is that with a broadcast, you send a packet which is received by all machines. So the hardware has to receive the packet, most of the time to decide that it's not for you. So it is a nuisance. Worse, if there are small bugs, if for whatever reason the software decides to send a broadcast whenever anything happens, then there can be problems in the network. There was in the past a famous case of the so-called broadcast storm, where due to one bug in one operating system, the version of Unix, whenever it received a packet of a certain type, it would send it back, the same packet. And it happened that this packet was a broadcast packet, so whenever it would receive this broadcast packet, it would send it back, which would, of course, all the machines would do the same. So you send one of those packets, then you have a loop of broadcast storms that would bring the network down, because it's flooded with all the traffic. So broadcasts have a bad reputation. You try to avoid them as possible in the LANs they exist. Of course, why do we have so much broadcast? It's because, again, of this idea. The mental model of the LAN is this one, the shared cable. On the shared cable, broadcast and unicast is the same. So there is not so much cost on broadcasting as there is in other technologies. Wired networks, even on Wi-Fi, broadcast is considerably more expensive than unicast. How do bridges handle broadcast? Remember, bridges are supposed to be transparent. That means whether we have this or the previous, that should be the same. Seen from the station here, of the protocol report, should be the same. So if one station sends a broadcast, for example, one station that is connected here sends a broadcast, then it has to be forwarded to everywhere. The bridges have to do it. We've seen that the bridges build a tree called the spanning tree. Therefore, it's very easy for them to send the broadcast. The problem with sending broadcasts in the network is if you have loops in the topology. But the bridges disable the loops by disabling some faults. Therefore, it's very easy to them. Broadcast is managed by simply sending it to all nodes on the spanning tree. So whenever there's an ARP of one machine here, if this machine does an ARP, then the ARP is broadcast to all bridges and to all stations eventually. We have seen that in IPv6 we use try to use multicast instead of broadcast. Other protocols that are more intelligent, like iTunes, use multicast also. You can stream music from one iTunes library over a local area network using multicast. This will therefore needs to be handled. Now, how can you handle multicast? Well, the easy way is shown here. So how is multicast recognized? First, there are special types of MAC addresses that are multicast addresses. They differ by what is called the G bit, by group bit. If the G bit is equal to 1, which happens to be the 8th bit, which is awkward, to be simpler with the first one. So if the 8th bit in the MAC address is 1, it means it's a group address, which is the old word for multicast. It's not, it's a logical address, it's not the address of a given piece of hardware like a MAC address normally is. So, if I send a packet to a given multicast address, the host operating system has to instruct the Ethernet adapter that some program in the machine subscribes to this multicast address, and once instructed, the adapter will receive all MAC packets that have a destination that corresponds, for example, to this address here, which might be an iTunes streaming application. There are, for reasons that I don't frankly know exactly why, there are the following conventions. For multicast is in principle anything that has the 8 bit equal to 1. For some reasons, if it's an IPv4 multicast or an IPv6 multicast, which is practically the only multicast we will see, it has to be further refined. So an IPv4 multicast has this format. The first half of the address is fixed. For the IPv6 multicast, the first third of the address is fixed. And here's an example of a non-IP protocol, one of the very few remaining non-IP protocols that exists and is useful. Many exist, I just for example, the precision time protocol, which is used when you do high energy physics experiment or smart grid high accuracy measurement, and you transport the clock of a GPS signal at the MAC layer directly, because you need special hardware support to make sure the packets that transport the clock are not queued anywhere, but they are transferred at the speed that's beyond the hardware. You recognize multicast address because the last bit of the hexadecimal digit 1 is 1. How does a network, MAC layer network, support multicast? Well, in the simplest form, again, the mental model being of a shared medium, that is, it's business as usual. For multicast or unicast or broadcast, if you truly have a cable to which everybody connects, is the same, just the nature of the address that makes it different. If you have a bridge network and you have so-called non-smart bridges, they do the same. They will simply forward it over the broadcast spanning tree. If you have smarter bridges, then they can build a multicast distribution tree. Most bridges are not smart. Building the multicast distribution tree requires that the bridges are able to talk to the operating system here, which normally they don't, because bridges are transparent. Normally, in order to build a tree, the bridges need to know that somebody is subscribing here. So there is no MAC layer protocol for a bridge to talk to an end system. How can they still know, how can they still talk in some way? It is typically by observing the higher layer protocol. If you listen to iTunes here, at the IP layer, you will send an active message to the network, we'll talk about that a bit later, to say, somebody here has subscribed to this group. This is an IP layer message. In principle, bridges don't look at IP layer messages, but in fact, they will. They will see, oh, there is somebody that has sent a join message, therefore somebody is listening to this group. And therefore, I know that somebody is listening to an IP multicast group. Now, how do you go from IP to MAC multicast group description, the MAC address? Well, the idea is that the MAC address trace, Wireshark, packet capture, Ethernet IP trace. Here is the Ethernet ether type that says this is an IPv6 packet. We see in the IPv6 protocol type, which is called next header 58, which means it's ICMP. And we see the destination IP address is this, which is a solicited node multicast address for something that terminates in 011. If you look at the MAC address, the destination MAC address of this packet, what do you think about it? You click this. I don't have many answers. I'd like to have more. I close the poll. Let's look at your answers. Try to close the poll. And the majority, 3 is the correct answer. The MAC address, the only trick is that the MAC address writes by blocks of 8 bits, whereas the IPv6 address writes by blocks of 16 bits. So these are the last 32 bits. Of course, there's plenty of zeros here that are not written, 3 zeros. So the last 32 bits, if I write them in hexadecimal digit, will be FF010001. This is exactly what we see in the MAC address. This is how MAC address IPv6 multicast address are mapped to IPv4 multicast address. A few more questions to stabilize things on the MAC layer. The protocol type is Ethernet thread. What can we get out of it? And of course, no, this is incorrect, this is correct. The protocol type in the Ethernet thread says whether what's the upper layer, which is actually cannot be TCP segment, is always in an IP packet. You will know it's more intelligent question. We have a working environment with, we have a LAN bridge that works for IPv4. We switch to IPv6. Do we need to change the configuration of the LAN? More precisely, if you upgrade everything to IPv6, and it worked before with IPv4 in the LAN, will it continue to work in the LAN when you moved everything to IPv6? We need to change the bridge configuration. The answer is no, which means yes, it will work. So for the basic forwarding functionality, the bridges are completely ignorant of the MAC layer protocol. There's no exception for multicast, but if the bridge ignores multicast, IPv6 multicast, it will broadcast them over the spine, so it will continue to work. Of course, if you move to IPv6, many things are going to not work. For example, if you have a DHCP server in your LAN that works only with IPv4, and if your hosts are configured to work with DHCP, it won't work, but they can use Slack and this will work. Normally, in many networks, this is the example of a whole network completely unmanaged. Many networks are managed. That means there is somebody somewhere who can do remotely changes to the configuration, see what happens in the environment. Now, those management applications, they are applications, they are TCP applications, so they work on IPv4 or IPv6. So if you change to IPv6, it might be that those network management applications don't work. So things might not be as simple, but the take-home message is the basic forwarding layer, basic forwarding functions are independent of the upper layer, the MAC layer. And that's one of the main advantages of MAC layer today. It's ignorant of the upper layer. In enterprise environments, like at EPFL or the Ethernet network, practically invariably people use virtual LANs. Virtual LANs is the example of how bad things can become when you do things that are too complicated. It's good for Cisco, it's good for network engineers because things are very complicated. What's the idea of virtual LANs? The idea is, well, we have LANs because that's the basic principles of IP. For example, you might have a network with 3 switches. And for some reason, you would like that all the hosts that are in the blue cloud look like they are in the same LAN. Which at the IP layer will be visible by the fact they have the same subnetwork traces. Why would anybody want to do this? In principle today, we don't care whether I am in this LAN or that LAN, this address or not this address, does it matter? In practice, in enterprises, it matters because people are lazy, so they use rules like, in order to print in that printer, you have to belong to this lab, to pay the paper and the folder and this printer. So, in order to be allowed to send a print job to this printer, you need to be a member of the lab. How do I check whether I'm a member of the lab? Well, you usually go to the Tequila server and then look at the credentials in principle. But another way, a simpler way, is to look at your IP address. If you're in this lab, you're at this floor, you have this IP address. This and other rules are being extensively used in companies. So they are in some sense freezing the structure of Vlans by saying the Vlans mean something to the organization, which invariably is bad, creates a lot of trouble because you can have somebody who's for some reason has an office somewhere else. So one good way to do it would be to move authentication where it should belong, which is in the authentication server, rather than looking at the IP. Nonetheless, this is not a lot. And now there are concrete problems. Assume we don't have enough space at my floor, and one of the members of my lab has their office on the other floor, it still would need to be considered as belonging to the same lab. Cisco has a solution for that. It's called virtual LANs. It is this guy who's at the wrong floor and needs to be able to print on a printer which is on this switch. So, what will we do? Well, the idea is to add a logical identifier on top of the MAC address. We have a label in the Ethernet frame, and this label says in which virtual LAN we are. So this label is called VLAN tag. We look at the Ethernet packet format. Instead of the principle at this location, you should have the type of the protocol. Now, if the first 2 bytes of this type are special, this one, it means it's a VLAN tag. It is not saying whether this is an IPv4 or whatever. It's a label of the VLAN. It says whether it's blue, green, or red. And all the switches that support VLANs will consider that different VLAN labels belong to different physically separated VLANs. In principle, the host don't see that, so when your machine should not be aware of that. However, the network management application that configures in the enterprise these switches will decide that this, and that port, so those 4 ports, belong to the blue VLAN. Whenever the switch receives a packet and forwards it to somewhere, to anybody else, it will insert the corresponding VLAN tag. So for the rest of the world, it will be seen as a blue packet. When it will reach this guy, for example, then of course the VLAN tag will be removed from the Ethernet packet. So the host will not see it. If you do Wireshark, will not see it. You need to do Wireshark between the switches to see the VLAN label. So by doing that, if there is, for example, an ARP broadcast sent from this guy to what is the MAC address of X, for example, this ARP broadcast will be tagged with a VLAN. And the VLAN switches, at least as a mental model, treat all the VLANs as many separate networks, with one spanning tree for each of them. So there's a blue spanning tree, a green spanning tree, and a red spanning tree. Now the green and the red are very simple, there's only one switch. The blue spanning tree means there are 2 switches here. Which means if a broadcast is sent from this, it will reach X, E, and F, but it will not go to switch S1. It will not reach the green things, it will not even reach the switch, because this switch has nobody with a blue VLAN label on the center. So it will separate the broadcast domains, which is one of the main reasons, and it will also make Apple happy, because Apple doesn't like that you stream your iTunes stuff to the rest of the world. So if you stream iTunes, it will remain within this blue environment. So this is the story of VLANs. Quick poll to see if you understood it. So here is a zoom on the green and red VLANs. Now assume A sends a ping to C. A is on the green VLAN, C is on the red VLAN. So A has an IP address to send to C. S1 is a VLAN capable switch. What will happen? What should A do? majority thinks it's B, sends an ARP request in order to obtain the MAC address and the VLAN label of C. Which sort of makes sense, because in order to talk to C, you need to know the VLAN label. But it doesn't make sense, it's wrong. So the correct solution is this one. Why? Well, the red and the green VLANs are two separate LANs. When A in one LAN talks to C in another LAN, what do? On the MAC layer, it's impossible. Two LANs cannot communicate. If they communicate, there's a bridge and they are one LAN. You cannot communicate at the MAC layer from one LAN to another one. For this, we have the IP layer. So what should happen is, hopefully there is a router somewhere in this world, otherwise it will not work. So there must be a router, which mentally I represent as a box that is both on the green VLAN and on the red VLAN. Of course, it has only one physical interface, it is a separated box. And this router is the default router, for example, for A. A will therefore send the packet to R. R has to be on all the VLANs that it interconnects. So the traffic from A to C will need to go via the router and that. This is what VLANs do. Of course, now, if you are making your Cisco and you're making your product, you will put the router perhaps in the VLAN switch. And we'll say you invented a new product on the layer 3 combined switch to avoid sending packets back and forth. But the mental model and also the practical model in many cases is this one. In order to go from one VLAN to another, you can't directly, you have to go through parallel. Let's put all things together. To recap, we have seen physical repeaters, which are frequently viewed as intermediate systems of the physical layer. We've seen bridges and switches. Again, the word switch is very misleading. Switch means something that forwards packet in hardware. So a layer 3 switch is a router, a layer 2 switch is a bridge. Very often, bridge equals switch, but be careful. The interesting thing of bridges is, of course, that it can be used between different technologies. Ethernet to Wi-Fi, but also Ethernet to Ethernet. Ethernet on optical fiber at 10 gigabits per second to Ethernet at 10 megabits per second, etc. But this is not the way Wi-Fi is usually made. So Wi-Fi, as I mentioned, is mentally the same as CSMAC or Ethernet, with small modifications that are important if you're analyzing the performance of a Wi-Fi protocol. If you are analyzing protocols, the only difference of interest is that in the Wi-Fi header, there are 3 addresses. In the Ethernet header, there are 2, the source and destination. In Wi-Fi, there are 3, which are very cumbersome. I mean, the Wi-Fi standard is 2,700 pages, and so it's impossible to read. So they are very complicated names, but the names I give to them is you have the source MAC address and the destination MAC address, and an access point MAC address. Why an access point MAC address? Because the classical use of Wi-Fi, like in this room, where you have 2 access points, and if you look at the base stations about here, you see that they have an Ethernet cable. So the typical use of Wi-Fi base station is you have a Wi-Fi base station that has an Ethernet connection, and this is, and every traffic that goes from Wi-Fi to another Wi-Fi will go via Ethernet, but will go also via the base station. Now, if A sends a packet to the router, for example, called to G, which is all of this, if there is no router in this network, then we have a bridge network. So if A sends a packet to G, the MAC destination address is of course G. But in reality, the way things are done, A nature of the MAC protocol and the fact that the base station is a central point, it needs to know it's sending the packet to E and not to B. Because in Wi-Fi, if you send a packet, everybody can receive it. So B could receive the packet. It's called the ad hoc mode of Wi-Fi, which is very seldom used, but it can be used. But most of the time we don't use it. Most of the time we send to the base station. So this violates everything we've seen so far. When you send a packet to a destination, you don't write as destination address the intermediate system. At the MAC layer, for example, if this would be a bridge, we don't write destination address. But for the collision resolution protocol of Wi-Fi, we need to know who is the intended receiver for sending the ACK, for sending, you remember in Wi-Fi there's a CPS, RTS, all that stuff needs to know who has to do it. Is it D or is it E? Therefore, there is an additional identifier, which is just the MAC address. In that case, when A sends a packet, it will send it to destination address G, but to access point address E, which means it will be received by E at the Wi-Fi protocol. So that's the main difference. Questions? Yes?
Are there 4?
Not that I know. Not that I know, but we can discuss offline. I don't know everything. Last time I checked, there are only 3. Let's skip this one. Sometimes you hear the terminology non-routable protocol. You hear that in industrial environments. Here's an example. It's a protocol called SV that's used in substation automation in the smart grid, where you have a computer that wants to collect information about an embedded computer. And in this environment, very often, the people, believe it or not, have written applications directly on the MAC layer. So they don't use TCP-IP socket, they use MAC socket if you want, which is very clumsy to use, but it's been done, it exists. You can do it, because there's no reason why you're not able to do it, because although I would hate to say that, but the MAC layer is like the IP layer. The address format is different, the rules for forwarding and building the tables are different, but it still is the same thing. So you can build a network with only the MAC layer, and this has been built and exists. There are a lot of industrial networks that are just at the MAC layer. They tend to disappear because in practice, if you write software, you want to use the mainstream software environment. Now the mainstream software environment is to use sockets and even high layer abstractions, like you will see in that 3. So if you use lower level abstractions, you're going to use very special software environments, so it's not good and not very pleasant. So it tends to disappear, but it exists, still exists a lot. This is called an SV, which is an application layer protocol. In that context, in this use, when it's used in this way, it's called a non-routable protocol, which simply means non-routable means it doesn't run on IP. You cannot put a router in that stuff, but it runs on the MAC layer. Voilà, that's all I will see for the MAC layer. Perhaps a few more questions to, if you fit. Here is an example of a bridge between Wi-Fi and Ethernet. Web server M1 sends one IP packet to LA. We observe the packet at this point. What is the MAC destination address? course, if there's one thing you have to remember about the MAC layer, it's that one. So when you send a packet to the destination, MAC destination address, I'm not talking of the base station address over there. The MAC destination address at this point is M4. You're building a network at the MAC layer. When you send a MAC packet to someone inside the MAC layer, you put MAC destination address, the destination, and the final thing. When you send a postcard to me, because you're on vacation, you send me a postcard to say hello, you put the zip code, my postal code, not the address of the next post office in Italy where you're on vacation. You put the final destination. At the MAC layer, the final destination is M4. So it is this one. Same question now, if we have a more classical base station. In the previous case, the base station was connected to a bridge via Wi-Fi, which you can do, but it's very inefficient. It's very inefficient because all traffic will go twice through the base station. Most traffic is not local, and it's very rare that you talk to someone that's close to you locally. When you do that, you do it via Facebook or whatever, so you go to an outside server. So most traffic will exit here. If this is a wireless link, then the traffic will first go to the base station, then from the base station to the bridge, which will use the radio channel twice instead of using it once. In practice, it doesn't work well from the performance view. So we do this. If we do this, same question, what's the MAC address you see here? The MAC destination address. And it's M4, there's no change. This is acting as a bridge in principle. If it acts as a router, of course, the answer will be different. But if this acts, it would be very weird to act as a router. That would mean this is the default router for those guys. That is rare. But that can happen in all environments. Otherwise, of course, it's digital. Yes? How do we know if the base station is a router or a bridge? We don't know. The base station is typically the name of the box, or depends what you call a base station. Again, that's the difference between architecture and product. Router is an architecture name, it's a function name. Base station also is a Wi-Fi functional name, but of course it's also the name you give to the box that you buy in the shop, and it's the base station. Most base stations can work as routers, but they don't necessarily work as routers. Yes?
If my base station at home is connected via Ethernet, I'm sure that it's a bridge and not a router, right?
If my base station at home is connected by Ethernet, I'm sure it's a switch and not a router. A bridge and not a router. No, there's no reason. It could be. It could be a router. You have to look at the dock of the base station, what it's doing. You have to decipher the documentation, which will not tell you it's a router. You will see whether you need to configure subnet masks, for example. If it's a router, it will need to be configured. You will need to give subnet masks. Right? If you see no configuration anywhere, probably it's a bridge. Let's talk about a few security aspects. The purpose of this course is not to focus on security, but we'll still discuss the security aspects that are most relevant. At the MAC layer, we've seen that the MAC addresses are sent in the clear. There's lots of problems that may cause. Eavesdropping, we can hear, perhaps even if the data is encrypted, we can hear that you are here, that you're sending traffic. And we can perhaps more severely do impersonation. That means I connect to LAN, tends to be mean. So you have man-in-the-middle attack, or you can do worse things. You can also have free writing, which is, for example, I come to a room, I see an Ethernet socket, like the one that connects this base station. I unplug the base stations, and I plug my PC. And I have wonderful, high-performance Ethernet access. I'm not sure you should try, but perhaps it works if you do that here. But in offices at EPFL, you can do that. You come to an office, you connect, it works. Which is not very secure. EPFL is not a bank, so it's okay. There are solutions to that. The solution is called MAC, which simply says that we should not do just everything we said at the MAC layer, but in addition, we should have some security mechanisms to allow somebody to connect. That's called access control. And while somebody is connected, we can do at the minimum authentication. That means making sure that the packets that come are the ones from the machine that has been authorized, and perhaps even do encryption, where the goal here, I'll take 2 minutes of a break, where the goal is to prevent somebody from sniffing your traffic. This is not done on Ethernet, practically everywhere in EPFL. It is done on Wi-Fi. When you connect to the Wi-Fi network of EPFL, EPFL, first of all, you need to log in, you need to give your credentials. So that is the access control part. And typically, authentication and encryption are done. And authentication and encryption means that once you have given your credentials, there are secrets, encryption keys, are delivered to your operating system, and then all the packets, all the content of the packets is encrypted at the MAC layer, which means the packet sniffer will see the MAC header, MAC destination address, MAC source address, and the rest will be encrypted. So we will not even see whether it's an IP. It will also typically be authenticated. This being said, assume now Bart, who is an EPFL student, connects to EPFL and wants to give his access to Lisa, who is not an EPFL student. Because he took the first part of this course, he sets up his computer, his laptop as a bridge. Will it work? Seconds. And you think it will not work, which is always a safe bet, because complicated things don't work. If there's a good reason, well, probably it won't work. I mean, in TCP-IP, you never know exactly what the latest version of this software does. Infinite creativity, but in principle, the following thing should happen. If you go to this network where there is access control and authentication, then all the frames that are received by the base station are verified against the MAC address. So when you negotiate access to the network, MAC-sec functionality, you have to agree on a mechanism of signature, and then all the frames are signed, and the MAC the source MAC address is verified. This is to make sure that in principle only Bart can send traffic. This is MAC layer authentication, so the only thing that is watched is the MAC layer. Now, when Lisa sends traffic, the source MAC address will be Lisa's source address because the bridge is transparent. So when it goes over the Wi-Fi link, it will appear as somebody who is trying to use the credentials of Bart as a different MAC address. So the very likely thing is that the pull-off, the authentication will fail, the packets will be dropped. You will still be able to participate in the MAC protocol, but the packets will be dropped by the authentication mechanism that you use. It's probably a bad idea to try to connect this way. Now, Bart, who is smart, tried something else. That in this PC. I know how to do that. Close the poll in a few seconds. So again, we have to be careful about statements that will work, do not work. But in principle, it should work. It should work. Well, because what does a NAT do? Everything that comes out of the NAT, or this would be the binary side of the NAT, everything that comes out of the NAT appears to be a different process, or different processes running in this machine. So the tracking of these are, well, this guy will need to allocate the subnet prefix. We'll need to configure the HTTP server in this machine, or to manually configure the IP addresses. So if you do all of this, it will work. The IP addresses will be transformed here, and everything will appear as traffic that is sourced by this machine. In particular, MAC sec will do its job as a MAC layer. This is packet, but MAC source